Hello, this is a lecture on single-phase induction motors. Here we will introduce the single-phase induction motor and its operation in terms of magnetic field and torque generated. So to begin with, we will start with a comparison to the three-phase induction motor. So straight away, this is a representation of the three-phase induction motor and AC applied to the three-phase induction motor, whereby this represents cross-sections of the induction motor and the resultant magnetic field. That is the resultant magnetic field. This represents the stator. So we look at the change in the resultant magnetic field as the voltage changes with time. So that represents time in regards to the voltage and also the resulting. So like for example, in instant number 1, we have blue having a 0 value, red having a positive, and green phase having a negative value, in which case, due to the arrangements of the windings within the stator, the resultant magnetic field is in the direction shown. At point number 2, instant number 2, which is there, instant number 2 is represented here, whereby the resultant magnetic field is in the direction shown, and so on and so forth. We have instant 3, instant 4, instant 5, instant 6, until you return to instant 7, which is equivalent to instant number 1 over there. So the resultant magnetic field in a three-phase induction motor, when a three-phase voltage is applied to it, appears to rotate within the confines of the motor, such that it produces a rotating magnetic field simply because of the nature of its windings. Now, this phenomenon is dependent on the fact that you have three-phase induction windings wound together and applied to the motor itself. Okay, what happens when we have a single-phase induction motor? So if we now look at the cross-section of a single-phase induction motor, you find that it will only have one set of windings. Even if you have two poles, you would still have the same supply being given to the motor. So like for example, you would have an input there and an output being taken out from there. So in such a case, if we have the single-phase induction motor with a voltage being applied to it, you would then find the phenomenon of, for example, if we have it being applied such that the currents are flowing into on that side and out on the other end, this cross-section of the motor that we show here, the resultant magnetic field would be in the direction downward. All right. Now, what happens when you apply a single phase to a motor is that the only thing that will change is the polarities. So your only alternative would be either these currents are flowing into a winding or out. They can only be in one of two directions or polarities. So you will find that the resulting magnetic field can only be either, in the case of the cross-section that we have here, either in a downward direction or in an upward direction. Those are the only two possibilities. So what happens when this phenomenon is seen? That leads us to what is called the double revolving field theory. Now let me explain a bit further about what we are talking about. So we have already made the assumption that the voltage or the resulting magnetic field is in the direction shown, which means that in any particular instant, the value of the field is given by the value of the field generates a force due to the magnetic attraction or the field itself in that direction. And that is the resultant known as the peak, all right? Because that is the most, the biggest value of the field itself. It appears to result in that direction. Now, if we take this to be the axis of the windings, okay, the windings within the stator, right? Assuming that we have our currents flowing in the directions that are shown. Okay. So in this particular instance, we have the axis of the windings in that direction and the resultant magnetic field in that direction. Now, if we mount our rotor consisting of various bars, this is a cross-section of the rotor, and the rotor is only able, it's only free to move in the direction shown. Show it a bit better. So it's only free to move in that direction, all right? Either it will rotate clockwise or it will rotate anti-clockwise. Now, in either case, we still have our force, which is moving in that direction, acting on all of these parts of the rotor in the same way, right? So let's take, for example, this particular bar of the rotor, and let's call it A. The forces acting on bar A will be looking in this direction. Now we have F peak. Yeah, let's call this F peak. Right? That is the resultant. That is what we have called our resultant force, or due to the magnetic field within the stator. Now, the rotor itself is only free to move either in a clockwise or an anti-clockwise direction. So if we look at the position of bar A, yeah, which is at this point, at this particular instant, the only resultant force that can move that way is in that direction. Okay. So what is the value of FA? That is the force that acts on bar A and enables it to rotate either in the forward or clockwise or anti-clockwise direction, right? That force FA will be equal to F peak because it is acting in the same direction. Both of them are acting in the same direction. The angle theta between the two is 0 degrees. So they are actually parallel to each other. Okay. Now let's take another bar. Let's call this bar number B. Right. Now bar number B is, that is not very straight, but it represents what we are looking at. It is from the axis a certain angle. Yeah. Let's call it B, theta B, a certain angle from the axis of the windings. Okay. Now this bar B, if we represent it over here, let's call it bar B. Let's represent it like that. The resultant magnetic field, the force due to the resultant magnetic field, is still acting on that bar in the same direction that we had before, bar A, right? This is at the same instant, right? Now, the direction in which this bar can move is, let me use a different color to represent the direction. Let's say it can move that way or that way, right? It is tangential to where the bar is, okay? At any given point, the freedom of movement of any bar is tangential to its location within the rotor. So in the case of B, it is tangential in that way. So that means that the only force that can act on it has to act in that direction, okay? Either pulling it that way or pushing it upwards that way. And because F peak is going in that direction, we will have it going that way, okay? So for purposes of our illustration, let's assume that the clockwise direction is positive and the anti-clockwise direction is negative, such that if the resultant force is tending to move the point we are looking at in a clockwise direction, we assume that force resulting is positive. So let's look at FB, okay? So now FB, force FB is at an angle to F peak. Now we talked of the angle between B and the axis of windings being theta B, okay? Now if we look at it due to trigonometry, the same, or geometry, not trigonometry, that angle will be the same theta B. And in the case of this particular rotor, the rotor is divided into 4 times 4, 16 quadrants. So 90, every 90 degrees is divided into 4 parts, all right? So in this case, 90 divided by 4, let's do that calculation, 90 divided by 4, you end up with the angle theta B being equal to 22.5 degrees, okay? Now, because bar B is only free to move in the direction indicated, that is FB is tangential to the clockwise motion or the rotation of the thing, of the rotor, we can get the component forces that result from F peak. So F peak will have two component forces acting in those directions. One is acting outwards for FB, and one is in the direction of FB that we are looking at, right? So in this case, in this particular case, FB is related to F peak in what way? It is F peak times the cosine of theta. Therefore, FB is equals to F peak cos 22.5 degrees. So FB is equal to this cosine. It is 0.92, let's call it 4 times F peak. Okay. So the force that is acting on the bar B in the direction in which it is free to move is 0.924 times F peak. Okay. If we take an angle or a bar C, which is in a position such that, let's call it bar C, it is in a position such that F peak is in that direction, but it is only free to move at a 90-degree angle to F peak, right? What does that mean? FC, which is this one, will be equal to F peak cos theta. But our theta, C, is 90 degrees. So that means that FC is equals to F peak times 0. So now let's look at another point which is directly opposite from B. Let's call it D, which is located there. Now D has an angle of, which is measured from the axis there, theta D, right? We said theta B, let's call this bar D. Theta D is equal to 180 degrees away from theta B, which means it is 180 minus 22.5, which is 157.5 degrees. Now, in the case of bar D, so we have bar D represented there with the same F peak, which we had there. The freedom of movement for bar D is that way, right? Either here or there, which means it looks something like that, okay? Following on from what we had before, FD will be acting in that direction, whereby this is 157.5 degrees. That means, following on from what we had before, FD is equal to F peak times cos 157.5 degrees, which is equal to F peak into cosine of 157.5, which is negative 0.92 approximately 4. Now this is very interesting because we have 0.924 negative here and we have 0.924 positive in that location. What does that mean? That means that if you take FD, the force that's acting on D, and the force that's acting on B, they tend to be equal and opposite. And we can extrapolate that across the entire rotor and say that all points that are on each side of each other, all the forces acting on the left-hand side or the right-hand side will be directly opposite to those acting on the opposite side. So the forces on the right-hand side cancel out with the forces on the left-hand side. What does this show us? This shows us that there is a series of fields that is canceling each other out. Okay. Now, what else does it mean? This is also a representation of a pulsating field. Now, for the instances that we are talking about, we took a time t, right? Bear in mind that with time, the value of the force F peak, this resultant force due to a resultant magnetic field, will change with time, such that we have, let's call this our pulsating field. We will have the magnitude of the field or the magnitude of the force changing with time, but we will not have the direction changing. So it will either act upwards or downwards with changes in time, right? So in the general case, when we look at the forces, the force at any given point, F, yeah, the force on any point will be given by F peak times the cosine of the angle theta from that point to the axis of the windings. Okay. For the case of D, the bar was at 157.5 degrees away from the axis of the windings. If we take, a point over here, you will look at what is the angle all the way round to that point. And the value of the force acting in this direction will be F times the cosine of that theta x, if you call this point x. Okay. Now, this is for any given instant. So bear in mind that the field itself or the voltage changes with time. Okay. So F peak itself Yeah, the value of this force changes with time, and this is also sinusoidal. So it is changing from a maximum value in relationship to the cosine of the angular motion, the cosine of the voltage itself. This is the representation of the way the voltage changes when you have an AC voltage being applied. Okay. So now that means that this F peak, because it is changing within F, you have F being altered by two different components. You have the time component and you have the space component. So cosine theta times cosine omega t. Okay. But if we remember our trigonometry, we used to say that cos A cos B is equals to a half times cos A plus B plus cos A minus B. Okay. Now, if we use this identity, we will end up with F is equals to F max times a half into cosine theta minus omega t plus cosine theta plus omega t. Okay. Expanding this fully, we have two different forces acting on any given point. Yeah. Okay. Let's just erase that. Now, what this means is at any given point, the forces acting on it appear to be in two, there are two resultant forces, or there are two component forces that act on any given point. And we know these forces to be resulting from the equivalent of two different magnetic fields, because the total resultant force comes from a resultant magnetic field. So we call these two components the forward and the backward components, right? And these two components are very crucial in the action of, or in explaining the action of single phase induction motors, because you can resolve all the characteristics of the single phase induction motor into these two forward or backward forces. Now let's look at a familiar term that has already been brought up in induction motors before, three-phase induction motors. And let's look at the slip of the single-phase induction motor. So let's assume we have a rotor here, and that rotor is rotating in a given direction. So let's say it is rotating in that direction, right? Let's call that the rotor direction, and let's say the speed is given by n, right? The speed of rotation. In this particular case, you will have the synchronous speed going in that direction as well, right? Let's call that synchronous speed ns. Okay. However, we said that there are two different components of all the forces that are acting within the rotor. So what does that mean? You will actually have two different synchronous speeds. You will have a forward synchronous speed and you will have a backward synchronous speed. Okay, so these two will be ns in the forward direction and ns in the backward direction. So what does that mean? We will also end up having two different slips. So let's say the first slip in the forward direction is given by ns minus n over ns, right? And this is equal to the normal slip that we usually have. However, in the backward direction, okay, it will appear that our ns is in the opposite direction. So from the point of view of the magnetic field, the rotor is rotating in the opposite direction. The relative direction between the two will be such that you have a negative rotor speed, a negative mechanical speed. Okay, now let's rearrange this such that we put it in a different way. ns can be represented as 2ns minus ns, and then we have it as plus n. All right, now in this particular case, over ns. Okay, negative negative gives us positive, and we are introducing 2ns minus ns to take the place of this ns. We are doing a bit of mathematical gymnastics in order to arrive at something interesting. So let's split these two. We have 2ns over ns minus ns over ns plus n over ns. Okay, and that can also be simplified into 2ns minus ns. These two cancel each other out, and if we put these two together, you will have 2ns minus n over ns, like that. Okay, just erase this so it doesn't confuse us. Okay, so what does this mean? This is the same as that. Okay, so what we've said is the slip in the backward direction is equivalent to 2 minus slip in the forward direction. Okay, this is a very important phenomenon that we have achieved. It is equals to 2 minus the standard slip, right? This is a very important phenomenon because it helps us to explain why the double rotating field theory or the double revolving field theory explains the motion of a single phase induction motor. In order for us to do that, let's look at the torque of the single phase induction motor. Okay, now previously we had talked of the torque of an induction motor being given by 1 over omega s times I squared R2 over S. That is the current in the rotor times the resistive component of the rotor. Now, if we take when speed equals 0 at standstill, yeah, for example, when the motor is stationary or when the motor has not yet been started, n is equal to 0. What does that mean? It means that SF in the forward direction is equal to ns minus 0 over ns, which is equal to what? It is equal to 1, right? And similarly, SB is equals to 2 minus 1, which is still equal to 1, right? Now, in this instant, when n is equal to 0, yeah, the slips of the two SF is equal to SB, which means that the torque in the forward direction is equal to the torque in the backward direction, because they have the same value of slip. Now let's take an instant where it is in normal operation. So S is a very small number. It is much less than 0. Let's say 0.04 or something like that, right? It's a tiny number. SF in this case will be tending towards 0, right? And SB will be tending towards 2 minus 0, which is equal to 2. That means that the torque in the forward direction tends to be much higher than the torque in the backward direction, right? So let's call this normal operation. The torque in the forward direction will be much higher than the torque in the backward direction, simply because in the forward direction this is a very small number, so it means it increases the value of the torque, and in the backward direction this is a very large number, 2, and it decreases the value of the torque. So the torque in the forward direction overwhelms the torque in the backward direction. This is very important because we can see at standstill the torques cancel each other out. Okay, this is at standstill. However, at any other time the forward torque will be much larger than the backward torque. Okay, and that means that as long as the single phase induction motor is already in motion, right, there will tend to be a greater torque nudging it in the forward direction than in the backward direction. Okay, so as long as the motor is in a state of motion, it will tend to continue in that kind of motion. And this characteristic demonstrates or shows that if we are able to give the induction motor a push in any direction, it will start. But if it is at complete standstill with no force acting on it from the outside, it will not be able to start itself, and it will remain in that position even though you have applied a voltage to it. Now let's look at the equivalent circuit of the single phase induction motor. Using the double revolving field theory, we end up with the circuit that is shown as indicated. Okay, so what this means is you have the forward and backward parts of the circuit of the rotor being represented by two different arms of the rotor. Okay, this is because if you look at those two components, you will have the forward component and the backward component accounted for. Okay, now when we relate this is very similar to the per phase equivalent circuit of a three-phase induction motor. We have the stator components and we have the rotor components and the magnetizing inductance that we had in the previous three-phase induction motor equivalent circuit. Now, when we look at these arms that are introduced, we take into account the two forward and backward characteristics of the two. So, for example, you would look at the, let's talk of the circuit analysis. So, the values of the impedances, because we did the circuit analysis of the per phase induction motor, So the value of these impedances, which are indicated here and here, can be represented as follows. So ZF, which is the forward value of impedance, is given by an RF plus JXF, a reactance, a certain reactance F. And these are the equivalent of, if you look at that arm of the circuit, you have X2, JX2 plus R2 over S in parallel with XM. And this can be then given as the product of the sums, which is JX2 plus R2 over S times XM, and the sum of all those components. Okay. Likewise, for the backward component, you have R, a backward equivalent, plus J, a backward reactance, which is given by product over sum once again, R2 over, in this case, 2 minus S there, over the sum of all of those. Okay. Yeah, so that means we can draw an equivalent circuit, a simplified equivalent circuit that will look like this. So you have your R1 and your JX1, and then you have the equivalent arms. Whereby this is ZF over 2 and this ZB over 2, which is R2 over S, not R2, sorry, RF 2 and XF 2, then RB over 2 and XF over 2. Now the importance of this simplified circuit is that if you have the incoming current here and you know the equivalence of these two components, you can make use of your knowledge of that input that you have and the phase voltage that you know to do circuit analysis on the entire circuit. So that can be a useful circuit. And if we look at the power flows, similarly, these will be similar to what we had already encountered. So you have the same types of powers, you have the same power flow diagram with air gap power and converted power and so on and so forth. But in this case, each of the power flows has a forward and a backward component. So like, for example, air gap power in the forward direction will be given by I1 squared 0.5 RF, which we have just looked at here, that if you know this incoming current, you can make use of it for various other calculations. So in this case, we make use of RF, which we already know. And likewise, the air gap power in the backward direction, or attributed to the backward field, is given by I1 squared into 0.5 RB. Okay. Now, likewise, if you know the resistances, so like for example here, the RF only has an R2 component. This R2 is the only resistive component in the entire impedance there. So you can make use of that fact by attributing it to this RB here. This is something that we we made use of in the cut that we did for three-phase induction motors. And therefore, the total air gap power adds up the two forward and backward components. Similarly, when we look at torque, the induced torque is given by air gap power over synchronous radial or rotating speed. But we already know the air gap power up there, so these can be obtained from those components that we have up there. Okay. Other useful elements of the various circuits are rotor copper losses, which are simply the sums of the forward and backward components of those. All right, and PRCLF is equals to slip times PAGF, which we had over here, and PRCLB is given by air gap power in the backward direction. And finally, converted power, you can guess that this will also be in forward and backward directions. So it is induced power times the mechanical speed, which is also equal to induced times 1 minus s of the synchronous speed, right? Those ones are all standard and all doable from the three-phase induction motors. So that brings us to the end. We will then do an example explaining these characteristics.